Today we're going to talk about the composition of functions. There's two symbolic representations for composition. One is this little symbol. Looks like a degree sign, but it's where a multiplication sign would go. However, it's not multiplication, it means composition of f and g. I tend to prefer this other notation because composition is a process of embedding one function into another function so that you end up with this more powerful function that completes two jobs at the same time. Okay, so the process is kind of like a chain reaction. We start with an input, whatever the x value might be. And we plug that into the g function, which means it's the domain of the g function. That will give us an output. An output is a range of the g function. So we start with an input and we end with an output. Then we take that output and use it as an input for a second function. So here's where the chain of events starts to occur. Now we use g of x as an input or domain of the second function, and it will give us a final output and the final output is the composition of two functions. Generally speaking, the composition of two functions means you've performed two different functions on an input. So what we want to learn how to do is to find a single composite function that does the job of both individual functions at once. First of all, let's evaluate f of g of 5. We have two functions up above. Function f says to take an input and multiply it by 2. Function g says to take an input, multiply it by 8, and subtract 6. So I'm going to start down here. The first way to evaluate this is using a chain of events. I'm going to start with finding the value of function g evaluated at 5. That means I take the g function and plug in a 5. 8 times 5 is 40. 40 minus 6 is 34. 34. Let's try that again. So we started with an input of 5. We've got now an output of 34. Take the output of 34 and input into function f. Function f says to take an input and multiply it by 2. So we performed both functions individually, one after the other. Finding a composite function means we find one function that can do the job of both at the same time. So we do the same process I just did, but algebraically. We start by embedding g of x into the f of x function. And again, the f of x function said to take 2 times an input. The input is going to be the g of x function. So I'm embedding or substituting. I perform the algebra and I have a new, more powerful function that will perform the job or responsibility of the other two individual functions. To verify that, let's now find f of g of 5 using the new composite function, which says to take 16 times 5 and subtract 12. Same result from using a chain reaction process with the two functions individually. Now let's embed the other way. Let's embed the f of x function into the g of x function. The g of x function says to take 8 times an input and subtract 6. For the input, we use the other function, f of x. That's the substituting or embedding process. That's called my composite function. We can embed a function into itself. That means we're just performing the same function twice. So if the f function is to double an input, the f of x function's job is to double a function twice or quadruple the function. Hopefully that simple example kind of made sense. Last set of functions will require a little bit more algebra, but the same composition or embedding process. I'm going to embed g of x into f of x. F of x says to take an input and square it. Subtract 2 times the same input and subtract 15. The input is the other function. That's the function that we are embedding. That's the function inside on the notation there. Here we have some algebra that we have to do. We have to square the binomial. That becomes x squared plus 6x plus 9. Distribute. And finally combine like terms. That is a composite function. If I were to embed the other way, f of x into the g of x function, this time we're composing in a different order. The g function says to take an input and add 3. The input is the f of x function. A little bit easier algebra here. We just combine like terms. And although these two composite functions have some similarities, they are not equal. And that validates an important point, that composition of functions is not commutative. Addition is commutative. You can add two functions in either order and get the same result. Multiplication is also commutative. Subtraction is not, division is not, and composition is not commutative.